Hello, this is our ME416 Project 2, designing a cooling loop for MSU's High Performance Computing Center. This project was done by my partner Bradley Haskin and myself, Josh Hybeck. For a bit of background on the project, we were designing a flow loop, a pump system to help cool the High Performance Computer Center here at MSU. By using an already established reservoir that heats other buildings, this was where our source would come from, and our motivation was to explore an alternative route for better cost efficiency and changing the refrigeration unit. Some of the parameters given through Michigan State were that the High Performance Center produces approximately 0.6 megawatts of energy, and the reservoir's flow rate is roughly 10 to the 6 gallons of water per day. Temperatures that we had to pay attention to were the initial temperature of 56 degrees and capping this to an increase of only 3 degrees more, as well as the maximum temperature of the computers, keeping it at 120 degrees Fahrenheit. In addition, piping sizes had to be kept at 12 inches in inner diameter and the length of the heat exchanger at 25 feet.
We had a couple ideas of how to accomplish this within the project. The hot side fluids of liquid H2O and CO2 gas were possible options, both having a square tubing layout to increase ease of cleaning and disinfecting. The cold side mass flow rate was dictated by specifications of 10 to the 6 gallons per day, converted in kilograms per second. The hot side mass flow rate was altered to accommodate the necessary heat load. Inlet and outlet temperatures were set according to the specifications. For the H2O design, the overall length reached 23.45 feet, which is less than the 25-foot maximum length specification. For the CO2 gas design, the hot side mass flow rate increased to 20 kilograms per second to accommodate the change in CO2 gas heat load. Otherwise, the inputs remain the same. The overall length of the CO2 gas design reached 23.54 feet, which is slightly larger, yet still smaller than the 25-foot maximum length specification. Trial D references the H2O design, whereas Trial E references CO2. CO2 had a smaller shell inner diameter, but a longer length. The H2O design costs about $3,000 more than the CO2 setup. Perhaps most importantly, however, the H2O design yields a lower shell side and tube side pressure drop, increasing performance over the life of the design.
In conclusion, we found the configurations of both cooling systems to meet the specifications given, finding that CO2 was slightly smaller and cheaper, but H2O with a significantly less pressure drop. Potential suppliers we found were Perry Products Corporation, who manufactures customizable sizes for heat exchangers, and Hayden Industry, which also, in addition to making their own, are developing new technologies for these heating systems.